I mute myself between the streams. What's up, everybody? How are you doing? We're just chilling out. Made myself a milkshake, so we're just chilling out. Got lunch right here, just relaxing. What is up? I'm gonna disappear so I can drink my milkshake. What is happening, everybody? Just magical disappear right there. What questions do we have? 201, if you're here, feel free to swing by. 201's got some big assignments tonight. 320 has the test. Let me look in the background to see how people are doing. We'll see right here. Lots going on. Got some grading to do later. So got grading, got office hours. What is happening? Who all is here? I saw a few people are watching. Mubot is awake, but I'm going to reset Mubot. So let's wake up Mubot in the background. Mubot is waking back up in the background here. So Mubot's waking up. And we'll see how everyone's doing. But say hey in the chat if you are here, especially if you have questions. Let me know what questions you have. So what questions do people have right now? Mubot is awake. Here we go. What's up? Good to see you here, our friend from Bulgaria. William is here. I'm just grabbing my quick lunch right here. I'm just going to keep disappearing. What are people working on? What questions are there today? We're talking about conditions for regression to end class. And we were honored to have you here. We're talking about all the experience you bring from especially the medical industry, talking about just how you utilize statistics, and just it's very important. It's when some people are going into medical type industry stuff. So I think you said yesterday you need to know that people, hey man, good to see you here, Evan. You need to know that people are not kind of like overselling things, like pharmaceutical industries are not overselling their claims. And you have to watch out. One of the first concepts you mentioned, which is so important, which we so rarely talk about, is p-hacking. Do you know when assignment file will be graded, and will we be able to see how many of the non-free response questions we get right on the test, or we have to wait? You have to wait. I think I'm releasing the answers to the test on Friday, just in case there's any difficulties. Usually I try to like have a day where the test answers are not like out yet, but it'll take like a day, and then I should have assignment 5 graded tonight, I think. It's just going to take me probably a little bit of time. There's like 39 of them to grade. I think there's 39 to grade, and I was planning to do it last night, but I was finalizing the test last night, and there's only so many hours in the day. You learn that the hard way when you teach, is that you have like blank amount of hours, and you run out of time. So between, will we know any percent of our grade directly? I believe you do. I believe you know a certain portion of your grade right after you take it. It shows you except for the free responses. I should have got a straw. I believe you see everything but the free, or you see your percent without the free responses. So I go in and grade those pretty quickly. If you do want to know your grade, like if you don't see it, just tell me, be like, hey, Brian, what I make. I'll email back, and I'll probably be grading those because those are quicker to grade than the assignments. I wonder if maybe we start converting the assignments to Canvas assignments. That would make grading quicker, because then we could more directly do things between. By the way, I'm open for research collaboration. Oh, that'd be cool. Yeah. Well, my email is just bstevens@utk.edu. I don't do much medical research. My email is bstevens@utk.edu, and I don't really do any medical research though. We do. I'll show you one thing we have right here. We do have our research paper out. I'm working on the revisions to it. I'll put it here in the chat also. This is the World of EdCraft research papers. I love the title. And thank you to Dr. Andrew Lowe and both Dr. Sean Willems, too. Could you go ahead and choose between Pearson, and Spearman? Definitely. Let's do that next year. 2 references? Oh, I think that's because of the other papers, right? References, and yeah, so they reference it. It's 2020. Did we put it out in 2020? No, we put it out in February 2021. But this is our research paper right here, World of EdCraft. I'm not going to download it. I'm gonna view it. Sure. Not trying to increase my own rank, but sure. This is our research paper right here, which goes over what we do with online teaching. Goes over, Dr. Lowe's versus mine, and you can see me with long hair right there, versus Dr. Willems, like kind of our basics versus us teaching in the environment. And the 3 of us use very different strategies between how we do our online teaching versus the comparison of like studios. You can see like my studio right here versus Dr. Willems, which is in like a whole room. Dr. Andrew Lowe actually has 2 setups, and Dr. Willems actually has a light board. He's got a full scale light board. And so it goes over lots of different things. We're going to start pulling in more data for this. We've been asked for a revision, as people know how it goes. That was Dr. Andrew Lowe's welcome screen right there, which is amazing. He's got a cool like visual background, got some nice music. And you can go through a very long research paper. Dr. Andrew Lowe, again, really great stuff. And you go down to my section right here where it talks about like MuBot a little bit. I've broke it, and let's do Pearson and Spearman next. Is it broken? It's broken. Watch this. Oh my God. There's Brian Stevens, Stat 1, University of Tennessee. And this is actually the very beginning when I was first teaching online. And then you've got some kind of our cool intros and stuff. And we haven't done much boss battles, speed runs. There's Tiny Brian as Parrot, all this great stuff. Discord, all this great stuff. Yeah. And there's the reviews over time. So anyways, let's hop back here. Awesome. I appreciate that. We're trying to... Drinking my lunch right here. Trying to create a good experience. Let's hop over and do some learning now. Let's go over to Pearson versus Spearman. Pearson versus Spearman. Okay, with Pearson versus Spearman, what is the main goal of Pearson? When you think Pearson, what are you thinking about? So this is your key stuff for Pearson right here. Like Pearson is mainly meant to cover what? Like what is the main goal of Pearson? Like you're gonna start walking away from Pearson as this point goes down here. Like it'd be great if this point's over here, sure, whatever. But this point going further out here is going to be problematic. As with if we see some of the scatter start to increase, like if we start to see this, that's going to make it bad. Also, we wouldn't want to see, I can't really change the line, but we don't want to see a nonlinear relationship. So what do we mainly see with Pearson right here? Like, this is not going to be that big of a problem. The further out this goes, the more problems that is for Pearson. Because literally we have Q, 2 quantitative variables. A straight enough relationship right here is highlighted by the yellow line. We want to see that the relationship here is straight enough, follows a linear pattern. We have here no outliers or no extreme outliers, so we want to move this point in if it's better describing of a Pearson relationship. And then we have here the plot doesn't thicken, which is homoskedasticity. So homoskedasticity means equal thickness throughout. Homo meaning same, thickness, so skedasticity. Well, here you see heteroskedasticity. It's one of my favorite words to say right there. So with heteroskedasticity, you're seeing an unequal spread right here. The heteroskedastic relationship, hetero meaning different, is going to show differing spreads. So a heteroskedastic relationship has a differing spread. Well, this is no problem for Spearman right here because Spearman is going to kind of not take into account the unequal spread of the relationship. It's just turning these into ranks. Better yet, when we turn things into ranks, if there's an extreme outlier like there is down here in the bottom corner, sorry about that. If there's an extreme outlier, it's going to downweight that outlier. But one thing is true that these relationships must be monotonic, but they don't need to be linear for Spearman. Spearman is going to help us out with this non-linearity, but you notice it's still monotonic. What does monotonic mean? I'm going to take a break, drink some shake. What does monotonic mean? Oh, now I'm reappearing. I thought I was gone. What does monotonic mean? Monotonic means all of these relationships do what right here? Every single one of these do what? All of these relationships do what? Because they're all monotonic. Like this one above me right here is monotonic. And you can see that's monotonic if you look at right here, just the stream of the points, one direction, yep. And it can be monotonic negative. These are all monotonic positive, but it just means it goes in one constant direction. Like, trick question. What should we use right here? Spearman or Pearson? And this goes to the kind of last two things we mentioned. Exactly. I say that all the time. Like, maybe you caught that one of my streams, One Direction. I always ask them their favorite band. I'm like, what's your favorite band? And people be like, Tool, Ben Folds. And I'll be like, no, it's One Direction. Neither. This one right here is not going to, the relationship's not going to be well picked up by Pearson or Spearman. And we were looking at this today in class with the code. We wrote code that created a kind of a parabolic relationship right here. If you look at this last bit of the code, this is the equation of a parabola. If we just do this, we will just get the parabola. Now you might say, well, why are you not just doing a parabola? I want it to have some randomness on it. So I'm putting randomness on the points. There's 201 points generated here. I'm doing a normal distribution. It's going to randomly choose a number for me that has a center of 2000. Actually, I don't even need the center. What matters more is just the standard deviation. The standard deviation is just going to create variation within these points. So we're not going to get a perfect parabola now. We're going to get these variations. And every time I do it, it's going to generate. I could make it vary more by just adding this. This is going to look a little crazy now probably because we've got a ton of variation. Yeah, you can barely even see the parabolic relationship right here because there's so much added extra variation. Let's cut that by a fifth. And now we have less variation. Of course, if we go way too small, it's going to look back perfect again. And we're going to see just too tight of a relationship. So this is just controlling the variation, the uncertainty around, because it's just doing random variation around the point. And all that really matters is the scatter, the standard deviation. So why am I doing this? Just so we don't get a perfect parabolic relationship. But when we look at this with the associate function right here, and we can see what's going on, we can see that the Pearson versus the Spearman, both of them come back with p-values that are very close to what? And then we'll go to this next one right here. Observe minus expected. Yep. That is the cell discrepancies. So the p-values right here are all very close to what? The p-values right here for all of this are very close to what? What are the p-values very, very close to? 1. Exactly. Great job. And what does that mean? That the relationship, the linear relationship here, and the rank linear relationship, because that's what Spearman rank correlation does, is it looks at the linear correlation between the ranks. It turns everything into rank values. It means that any sort of relationship in a linear sense, which if we were to plot the linear relationship here, we can take a linear relation, it's going to look horrible. If we look at the linear relationship, it looks like that. And so the linear relationship here, and you can look at the slope of the line too, which also indicates something to you. The linear relationship is likely what? The linear relationship is just likely what? Any linear relationship we see, and you can see by the bands around the, we talked about this today, the confidence interval for the slope of the line, you can see it's like, oh, it could go down here, or it could go up here, which kind of gives you an indication, and it goes through 0. We'll do another review question here in a moment. It indicates to you what? And it's weird. You're like, why are you fitting this? It's like, we could do another test here in a second, which would be a review from today. The linear relationship right here. Well, 1, this is not appropriate regression. This is not appropriate time to use Pearson. This is not appropriate time to fit a line. Because literally, if you go to the check regression, it's going to scream at you. Let's do the check regression, which we did today. And we're just kind of bridging topics. And interestingly enough, for the linearity, due to lack of duplicates or replicates sometimes called, I already forgot what was the highest we could get for the exam before the write-ups. I think low 40s, 41 or so. Did you get close to that, Ben? Let's say 41. Let me think. I think close to 41, like low 40s. I could double check if you really want in a moment here. But yep, flat relationship, and the slope is not significant. If you notice, the slope is just, the slope line looks to be 0. And you really see the problems over here in the check regression Normality of residuals is kind of bad. I mean, that's pretty bad. You've seen a little bimodality. Like the weavy pattern means a bimodality of it. Not the most of my concerns. The most of my concerns is down here. The spread looks to be about equal. Funny enough, we did randomness. Probably just more points indicates more scatter. Classic kind of more points will get more scatter. But the non-linearity. Now, the reason this is an issue sometimes, the way these statistical tests are performed are you need what are called sometimes duplicates or replicates to perform this test. So since we cannot perform this test, we need to look at the diagnostic plot because we don't get a p-value to check the linearity. And just this right here, 40 out of 50. Oh, out of 50, out of 50. Yep. Out of 50. And so, yeah, if you get a 40 on the test before I go through and do things, be very happy. The closer you are to 40, the better it is. Closer you are to 40. And what's interesting, here, let's do one right here. I'm trying to think of something good. Can't think of any good regressions. What is good data? There's so little like good regressions that exist, especially trying to find things that fit good linear relationships. You're welcome. Excellent work right there. Let's go look at a good regression. Our goal right now is to look at something good. And so I'm using the attach, which makes it so I get the autocomplete. It's a really nice feature. Attach, I'm going to predict somebody's weight from their desired weight. Let's hope people are actually kind of close. So I would assume people who weigh more want to weigh more. People who weigh less want to weigh less. Not saying they weigh exactly what they want to weigh, but there should be some sort of relationship right here. Which, if someone says, I want to weigh 200 pounds, well, then they might weigh close to that. Like they're knowing someone's desired weight would give you information about someone's weight. I'm saying that there is an association between these two. Let's look at it to see if we see this. And it looks like, oh, and that's so interesting. What? Okay, just what? Okay, come on. We're tossing this individual. We're tossing it. What do you notice right here? Come on, talk to me about this. Sorry, but that person's got to go. We'll remove them from the data set here. I'll remove them. I got a way of removing them. What's going on? Just talk to me about that. They're gone. Sorry, you gone. Why are they gone? I do not believe that person. Talk to me. Makes sense of that data. You always visualize your data. You always look at it and you say, nope, don't believe you. I'm not removing them because they're an outlier. I don't believe them. Yeah, they say they weigh 10 pounds, but they're trying to reach their goal of 0 or almost 0. They must have like forgotten to enter in a 0 or something. We can find them pretty quickly. They have the minimum desired weight. So you can actually go to which.min. Which.min finds the position of the minimum value in a data set, and they have the minimum desired weight. So since they have the minimum desired weight, I forgot my $sign. They are row number 5, which actually is nice because we can actually go and view them pretty quickly now. This individual right here is a male who currently weighs 16 pounds, but they really want to get down to that 6-pound weight group. They're a senior. You know what's going to be even easier? So we saw a little bit right there, but we can go right here to survey 9, and we could go right here to row 6 only, and here we go. Wait, row 5. Whoops. You know what you can do? You can actually go and just put the which min in there, because that returns 5. So rather than trying to remember things, which apparently I'm not good at right now, you can put the which min, and now we're returning 5 right there, or the row number 5. I think they say that the number of drinks they have at a party is 100. Come on, they had their first kiss at age 3. They study 24 hours a week. Good for them. They're doing some hard work right there. Yeah, I don't trust this info. Trying to think other things that look crazy. They drive a 2011 car, and this survey was done in 2009. So they're from the future. I hope they don't meet their goals either. That's kind of an unrealistic goal right there. They work out. I don't know if that's weekly workout. They work out 168 hours a week. I mean, You got to be that thin. They spend $100 money on a haircut. They have $1 in the bank. They've only downloaded 3 songs. They sleep 24 hours a night. They missed 150. Well, they're sleeping every night. They think their average attractiveness, hopefully that's out of 100. They've seen 1,000 movies in the theater, and they work 168 hours a week. Did they literally put in the maximum? I know. I think, you know what I'm going to do? Watch this. Survey 10. There's a few ways we can do this, but I'm totally just banishing that person. I'm going to call this correct. Let's call this, correct or something. We're going to go right here, and we're just literally going to take the same code. And what this code will do now is, one, if I do it now, it'll only put this person in here. So now it's only that person, but now I can go here and say not that person. So if you just look at the 2 data frames I've created right here, I've actually just subsetted, or rather removed. I mean, it is a subset technically, but I'm just removing that individual. And if this all looks really complicated, all I'm doing is just removing row 6. All that, or 5, sorry, whoever person 6 is, I'm finding the wrong person. So person 5 is being removed, but rather than putting in a number, which you put in the wrong number, you remove the wrong person, we can do it with code, and we can find that individual right there and remove them with code right there, which is going to be more consistent than putting in a number. So we've just redone this. Let's take our code right here. Let's revisualize the model without destroying our data. And we're going to go down here, and we're going to use survey 09 corrected. And let's fix the plot margins so we can do this. And there we go. I think there's a few... what is the most apparent issues with this plot right now? This plot does have issues. And it kind of makes sense. It makes sense when you think about it theoretically speaking, about people who desire to weigh less. And then as you go to people who desire to weigh more, you kind of see it. So you can especially see down here in the people who want to weigh 100. What do you know? I see it pretty clearly. It's going to be very apparent in the residual plot. It's probably the biggest problem. Yeah, you see it. That's, yeah. Oh, wait, what? What? Who you? This is one issue with our code. What is that person doing right there? Sigh. So we have a new person, a new Joker. Okay, let's find out about you. A random person who's trying to make fun of my survey. So this person is row 6? No. Really? Really? They have a weight? No. Oh, I'm still doing survey 9. Sorry. There we go. Okay, row 4? That close? They're like right next to... Yeah, they weigh 147, but they really want to weigh 63 pounds. This person right here, we're confirming it is this individual. So in truth, what we want to do is... I mean, we can still do it this correct way with our coding, but I'm just going to go the easy way and concatenate, remove 4 and 5. And now we're going to relook at the model. And here we go. I personally don't believe that somebody weighs 470 pounds and wants to get down to 70 pounds. Theoretically, let me look at the numbers again. 472 and they want to get down to 63. Theoretically, this person could exist. Do we have height? We don't have height in here. Theoretically, someone could be close to 500 pounds. And then you'd have to ask yourself, theoretically, we are hunting down for those outliers. Now, here's the big question. You are correct. I don't like this person either. If you look at this person, they're kind of our new maximum. They're the max on the weight. So let's take a look at the plot. This is going to be a big question, a super important question. This is our new maximum right here. They weigh like 300 pounds. They want to weigh about 160. We can go find them. We can do which.max of our corrected data. This is a very important question I'm about to ask because the rules are about to change and they have the maximum desired weight. They're row 104. So let's go to survey 10 corrected. Now my question is, I don't like this person. They're a bit of an outlier in my data set. Probably a symptom of the heteroscedasticity too. This person right here weighs 285 and they want to get down to 160. Can I remove them? Ooh, we can trim. Talking about some trimmed mean stuff right here. We can trim 5% from the top of the bottom distribution. We don't worry about it. We could, especially when you're doing like means and measures of center, you can do like trim to means. So trim means going to remove your outliers. So trimming, and we don't talk about that much, but that's a great answer. Like this is, I love having your insights right here. And the big question right now is, can I remove this person? I think they theoretically could exist. They're a female. They make much more logical sense to me. And I mentioned something big right here when I was talking about the theoretical existence of this individual. And then the really crazy one that we especially needed to talk about was the theoretical existence of this individual who currently weighs 16 pounds and wants to weigh 6 pounds. Can I remove, and this is a 201 question also, can I remove this individual? Remember, if you go back in time with what we did right here, go way back in time to the start, I removed this individual, and then I went in and removed this individual right here. So I removed 2 people already. Now my question is, can I remove this person? Should I? I mean, I can always do it, but should I? Should I remove this person? Good 201, 320 question. It is subjective. And that's so, but why? And so I don't think we can either. I totally agree with that. 100% agree. Why was I able to remove, especially going back to the beginning, this person over here? Yeah, exactly. You don't want to just, and you're Emin and also, can I call you, we'll just say our overseas friend. Let's see. I don't know, because I'm going to fear I mispronounce your name every time. Why did I easily just say, nope, you're gone to that person? I'm not removing them because, well, they also follow the relationship. The person we found second didn't follow the relationship. So this person up here does not follow the relationship we see with the linear trend of the data. And I'm not removing them because I don't like that they don't follow the trend. I'm removing them because I just don't find them to be theoretically possible. Once again, to look at their data, like third time here, their data suggests that they weigh 472 pounds, that's their weight on the y-axis, and that they want to weigh 63 pounds. Yes, I do believe theoretically someone can weigh this much. If it's clear, then we have errors in the import in the data process. Okay, exactly. That's exactly it. We had a data point right down here, which looked like an error. We had a data point up here, which looks like an error. And those are the clear removals. There is some subjectivity, and that's really a great thing. If it's really subjective, like if it's really borderline, then you might do your analysis with and without, and you always make note of that to say an analysis was done with the outliers removed and yielded the following results. So if there is a clear, I don't think someone's weighing 500 pounds wanting to get to 50 pounds, there's some error in the data right here. I don't know how to fix it. We can't go back to the original data. At that point, you can remove them. And you probably might even note that 2 individuals were removed from the data set with the following values, deemed to be, blah, 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 blah. You always want to be as clear and transparent with your data process as possible. We're not going to remove this person who's right above my head right here. They're a bit of an outlier. It's also a bit of the heteroscedasticity symptom. You can see right here the tightness of the data. You're seeing a stronger scatter of points. As you can see, the scatter is much greater up here with fewer points. And this is really showing up in the visualized model. Visualized model shows it, and the check regression shows it. Let's expand a little bit over here for our check regression. So yeah, this is, and also the non-normality of residuals, a lot of high residuals up here. And I say don't look at the histogram, but the histogram is also showing the extreme skew. So it's no shocker to me that we fail all the tests. But the least of my concerns might be the linearity of the model, which is really the backbone of the model. This is not a great model. It's got major problems. How practically significant is this model? Really good review right here. Is this model practically significant? Why or why not? Take a moment and think about it. Respond in the chat with, is this model practically significant? You might want to first think about, is it statistically? And the answer for that should be super clear. Is this model practically significant? What? Yeah, let's do it next year. You got it, Emin. We'll do a practical significance, and then we'll go over the criteria for passing them. We'll do the step-by-steps we did today in class. So what would you cite to me for the model's practical significance? And there are issues This model, all models are wrong. I think our friend might know that. Famous saying in statistics, all models are wrong, some are useful. This model's definitely wrong. Oh, yeah, it's definitely, yeah, we got some statistical significance. Once again, we don't care about the intercept. The intercept is statistically significant. That just tells us the intercept is most likely not 0, or we have good evidence. But the model itself, which is the p-value of the slope for simple linear regression, is very, 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 very statistically significant. The ratio of the estimate to the standard error is going to give us the t statistic right here. So we are seeing strong statistical significance, not by the t rather, but larger t, smaller p. And so this very, very small p-value is indication of extreme statistical significance. So this model is statistically significant. Is it practically significant? Like if I told you I want to weigh 170, I don't know what I want to weigh. I like fluctuate. I'm almost 180 these days, and I'm like, maybe I want to weigh 170. I don't know. I did some calculations, and I was like, apparently that's my optimum weight to be at like 14% body fat. I don't know what kind of doctor you're. You can tell me if 14% body fat's a good idea. I think I'm at 24% body fat right now. I don't know. So is this practically significant? Now, whenever you do practically, we need will here. However, model itself, it's not practically. I think it might be, though. Because if you know somebody's desired weight, it gets you almost 77% of the way, or almost 77% of the information. There are issues, like that's the worry of using this model for practical purposes, is that, you know, we do have some heteroscedasticity, more worried about the non-normality of residuals too, with some extreme points. I think it's probably people generally want to weigh more about it. Correct. Like knowing somebody's desired weight would get you 77% of the way. I'm rounding it. 77% of the way to understanding the variation in what they actually weigh. Like if I have a friend who says, I want to weigh 200 pounds, that would tell me a lot of the information about how much they currently weigh. Does that make sense? Like if my friend supplies to me the information of their desired weight, it would entail, like, I would expect 77% of the information in people's desired weights gives you the information. You'll just... Oh, you're killing me. You're killing me. I'd probably be in the American Army, and I don't know. Thank you to those who give their service to their countries, and I definitely haven't made that sacrifice that some do. That I have cousins who have, and uncle who has, and my father was almost drafted for the Vietnam War, or at least not too far. And then when we predict somebody's weight from their desired weight, and think about this, Brian said he wants to weigh about, let's go 174. Low 170s. I don't know. It just sounds crazy to me. I'm like, I don't know. I've gotten that low before. I'm like, you're too skinny. And I currently weigh, so that's my desire. I should have put that as desired. I desire to weigh 174. Sure. And my weight, you got to watch out, because that's certainly stored. Current weight is 186. How much do we miss Brian's? How much are we off by when we know Brian's desired weight? So we know Brian's desired weight is 174. How far is Brian's current weight off? And you could check this on yourself, see if it's accurate. Now, it doesn't mean we will miss by this. Gotta be careful. You don't say we will miss. But we typically miss by about this amount. Like on average, plus or minus, a little more sometimes, a little less sometimes. Knowing somebody's desired weight, like we know Brian desires to weigh 174, then we're typically off on his predicted current weight by about 17 or so pounds. And that's not that, I mean, is that a lot? That's where the debate comes in for practical significance of the model. So the residual standard error is literally, and we've got a graphic up for that right now, and then we're going to hop over to the other question. The residual standard error is the uncertainty in the residuals. So when we talk about residual standard error, we're talking about root mean squared error. And to our friend right here, do you use like mean absolute error? So sometimes people do it as MAE or MAPE, mean absolute percent error. Just wondering what you use for like your typical miss the model makes. So when we're talking down here about the residual standard error, we're talking about a small residual standard error would say that the typical miss our model makes in terms of residuals is rather small. But if we have a larger, this is still RSE, it's still the same thing, how we're using them right here. Root mean squared error is basically just your mean error. We square it because the errors are positive and negative to turn them all positive. We mean it because we're taking the average, and then we root it to bring it back to units of the problem. So when you look at root mean squared error, it's usually about a half width of the distance of the points. And so you can see this right here if we look at our model. Let's go look at the visual on it. If you go visualize the model, I should have done this beforehand because it's going to cheat now. If you go into here to the model, gotta make it really big to see it. If you go halfway, you see this goes to about 130 right here, maybe 135. So 100 to 135, about half of that width, which we do see a problem right here with the heteroscedasticity. We use RMSE. RMSE is going to weight heavier on outliers. So if there's issues with outliers, RMSE is going to inflate, which is a good thing because then it's going to be like, hey, you got some outliers there because you're squaring outliers. So an outlier, when it's squared, is going to be a lot bigger. So MAE does not take into account as much outliers. It's just a debate on what to use. Some statisticians going to be like MAE, MAPE, RMSE. It's just different metrics. It's like, I like Coke, I like Pepsi. And it's like, well, Pepsi's good, but you should like Coca-Cola. It's just a choice, just a preference at this point between MAE and RMSE. Either or is fine. We use RMSE also. Doesn't matter. I think there's like a metrics thing. There's a metrics package. And then we're going to take the next question here. I don't have it installed right now. I think it's metrics. Let me see if it downloads. I don't know what I'm downloading. We'll find out. There is no metrics package. Is it capital? There is a metrics package. What did I just download? I don't know. Let's find out. Is it what I thought? Oh, it is, I think. Yeah, look, MAPE. Wow, the things I remember that I don't remember. MAE, so we should get RMSE. Will it calculate RMSE of a model? I think it actually takes the actuals and the predicteds. It takes actuals and predicteds. So you actually have to put in here your actuals. So we're using the corrected data. We're predicting weight. So much work. Why can't I just put in my model? And predictions from the model. And there we go right there. And is it giving the same exact value? 16 point, and it is doing it slightly differently. Some people use small little corrections in it, which really bugs me. But you could switch over here to MAE and stuff like that, or MAPE, mean absolute percent error, all these different things right here. But all these metrics, the metrics package will calculate all of these. And you could, of course, read up on them if you're wondering about what MAPE is. We can go over here to the MAPE function, and you can find out about mean absolute percent error. It computes the average absolute percent difference between two numeric values, and just showing how it's calculated right there and what's going on. And you can, of course, look over our classic RMSE, computes the root mean squared error between two numeric values, and shows the values right there. Good stuff. I think, what was the next question? We can go over the test criteria. Let's do that. Let's do it in a segment right here. Take the last little bit of my drink. Okay, let's go over doing the test right here and see what we know. So when we do the test, let's make a new model right here. I was trying to find a good model. We're going to open up the data frame right here. This is where you can switch between your packages, your data frames. Usually you want to stay in the global environment. So we're going to look in the global environment. I've got currently loaded in data survey 9. Now, I've also attached it. Attached means that you can view the vectors in the global environment. I've already attached them many times, so it's giving me like a, hey, did you know you already attached these already? So they're already there. That means if I were to type one of the vectors in survey 9 just out normally, it's going to autocomplete because they're available in the global environment without actually having to connect the data frame to it. So you get the same response right here with the attach function, which makes them available in the global environment without having to reach into the data frame to get them. It's pros and cons to it. So with this right here, let's see here. We're trying to make a regression, so we need some quantitative variables. We got lots of factors right here. Now we could do regression, but not the type we're doing right now. Let's see if, a lot of them, someone said negative. Let's see. A lot of these are just going to be so bad, I already know it. A lot of these are really weak relationships. Like, I want to find something that's really good. And you have to go for boring stuff a lot of times. Like, really boring, like height and weight to find things that really work. Money and age. Yeah, which one was money? Great. Thank you for the suggestion right there. Which one was money and age? Let's look at that. Do we have age right here? Where's the age? We got age of first kiss, but do we have age? Tell me the variable names if you see them again. There was like money in the bank account. Money in the bank. So let's see if we have money in the bank. So there, we're going to try to explain how much money people have in the bank account. I think negative 999 might means they don't have a bank account. We have, when do people want to have kids by? When do you want to be married by? How much do people drink? So we could look at, how many drinks you have versus money in the bank account. We have NAs in here, which means someone did not answer, which means they just don't drink. So when did your parents get married by? Did you see the other variable? Do we have an age variable on here? I thought we had age actually. Here, we'll go to names of the columns. I need to do a grep on the names. Grep will do a search. Am I going? I thought there was an age on here. Should be able to do grep. I don't use grep nearly enough. Pattern, age, vector. Let's go names. Names, survey 10, survey 9, integer 0, because age is not in there. No, is it capital age? Yeah, it's case. You can put case equals false. So the only one that age appears in with grep. Grep's a great way to search. It's just a kind of control F through it. And then we could do case equals false. So we're just kind of, is it not case? I forget how to use mod grep. Ignore case, that's what it is. So we need to do ignore case equals false, but so we could do ignore case equals true, and now it'll find age. So let's see if we can find something related to, well, days per week you drink alcohol. Here we go. So here we are with predicting how much money someone has in the bank with how many days per week they drink alcohol. We're going to do here y tilde x comma data equals. So can we predict how much money someone has in the bank via how many days per week they drink alcohol? And the answer is the model looks really interesting. Well, the scale on this model is very interesting. I mean, there's just a huge problem with this to begin with. I mean, the answer to the problem with this, so this goes to, I think Emin was asking about, I mean, I can just tell you the problem with this model. There's a humongous problem with this problem. And what do you notice? And actually, this will branch into like a top. We'll use this to kind of go into it. But on the check regression, something's going to scream immediately. Go and drink some wine. We had a question one time, like, what is your drink of choice? And of course, drink if you're of age and drink responsibly. But there's the big, what problem do you see right here with the line, which has, what is the main condition that is just screaming to me right now? What is the main condition? So it's days per week you drink alcohol. And there is an ordinal pattern to days, or, well, it's integer pattern. The days are integer, which is, the y is kind of integer too, if you're doing like whole values of dollars. And there's some sort of scaling issue. I think someone must have reported some ridiculous value because we're getting a really crazy range right here. And I think Petrie has his code, which is one of the few things I don't like about reg class. I'm gonna plot it just so we can see a better view. Someone reported that they have, I gotta remove this person again. And actually that might be where the issue is coming from. Yeah, that might be it. Do you see how crazy the line is? The line might be getting destroyed by this person. So we need to find the max. This is what you deal with when you deal with regression, is you deal with this kind of stuff. So the money in the bank, and I love that it always auto-completes. It's person number 4. Thank you, person number 4. You know what? We're just going to survey corrected because that removes the crazy people. And now we've got this person. I don't know. They're going to hurt the model too. Model still's got problems. So what is apparent right here? And it should be most apparent over here that the line is not going through the center of the data. There might be some equal spread issues, but really the best way to look at this, and the line looks a lot flatter now. The best way to look at this is with the check regression. So let's do this step by step on the check regression now that we have something to work with here. Well, step 1. Yeah, they are probably creating the relationship. Outliers can do anything. And where is the only? I am shocked by this. I am absolutely shocked this came out this way. So this is so for Emin and everyone, and this is like the Shapiro-Wilk. You probably know the Shapiro-Wilk. This is the Shapiro-Wilk test right here. The name of it truthfully doesn't matter. Thank you, Shapiro and Wilk. But the name of the test is not so important. It's just a test for normality on the residuals. And what is this telling us? It's not important the name of the test. It's important to understand what it's telling us. And this goes back to the notes from today when we were talking about the steps. And the first step we do is check the p-values in my horrible handwriting. So we're here on the first step looking at this, and we're checking the p-value. Apparently. And what does this mean right here? That the p-value for the normality p-value came back as 0. Is this good or bad? Exactly. This means we reject the null hypothesis that it's normal, because that's kind of like I just call it, it's good. Like when you do assumptions, your starting assumption is that it's good. So we are going to have a starting assumption that it's good till we have evidence it's bad. It's the most general way to talk about these tests. More specifically, and the notes do mention that when we do the Shapiro-Wilk test on normality, we want to have a p-value greater than 0.05 to pass the test. The name Shapiro won't matter. I'm not going to put that on the test. When we do the test for equal spread, well, we want to have a test value greater than 0.05 to pass it. When we do the test for linearity, we want to have a p-value greater than 0.05 to show that it's linear. Looking at this right here, this would have a p-value of something like 0.00001 because there's evidence of non-linearity. That's what the low p-value means, is we failed the test, i.e. we have evidence that there's an issue. The assumptions are bad. So when we look at it in this sense for our plots right here, let's try to log the memory. And what does it try to log? You want to take a log of it? Yeah, let's quickly. We can, yeah, that's a great idea. Here, we'll do that next. Yeah. And you see, so we fail this. So due to this extreme value, great advice, we're going to try to log this, and logging it's going to take in the observations and create this person's going to have less of an extreme value. So can we fix this with a log? Well, let's find out. And then we'll try another way. So we'll have two ways of trying this right here. I think I can just log around this. Let's try log 10ing around this, or I might just save a transformed variable. It doesn't like that. It's mad at me. Log 10 does not, oh, because I did it in the wrong spot. That'd be true. It doesn't like that. What I'm going to do is I'm going to take the variable, and I'm going to go right here. I'm going to append onto the data set this version, but I'm going to call it log. And then I'm going to go log 10 of the variable. I'm going to put the variable right there. That creates a log 10. I'm going to grab the variable name right here. I'm going to pop the variable name in there. And then, did I not run that? Am I going mad? Maybe I am. Did I not call it the same thing? Oh, because I'm saving in the wrong spot. Never have two data sets with similar names. There we go right there. And log 10 still not found. I thought I saved it in. 2 seconds. Null? What you doing with that null right there? Let's go here to survey 10. Let's look at what's going on. This code's not running. There we go. We're getting NANs though. NAN stands for not a number. So you know what we might have to do? Really interesting with these values. Do you know how to fix this? This is actually a 474 fix. Emin, good question. Let's focus on Emin's question, then we'll go back. So Emin, why would we not want... So let me point this out, and let's focus in on Emin's question right here. This is when p-value less than 0.05. What is the starting assumption right here, Emin, with all of our hypotheses? And this is where the confusion usually is. When you have these assumptions right here, what is the starting assumption for linearity, for normality of residuals, for equal spread? Your starting assumption is what? And then we've got a really good kind of 474 question coming up here next. What is your starting assumption for all of these? What is your starting assumption for all of these? So look right here how it would work if you have a p-value greater than 0.05, which means you do not reject the null hypothesis, and a p-value less than 0.05. Your starting assumption, Emin, would be what? Your starting assumption for all of these is what? The very first starting assumption, what we start out with, go to lecture screen. The very first starting assumption is what? What you believe until you have evidence otherwise is what? So like when I look at this result right here, what do I believe about the linearity of the model till I have evidence otherwise? So I have high p-values here. And what do I believe about the linearity of the model till I have evidence otherwise? What is my null hypothesis for the linearity of the model? What do I believe? The model's good. The linearity is good. What I'm saying is right there with everything I've highlighted, that the model, which is the X variable itself, I'm assuming right now that it has a good linear relationship. And so I do not reject the null hypothesis. My starting initial hypothesis is that everything is good, and I do not have evidence of it being bad. And so we don't want to see these low p-values right here because that means there's evidence when we do tests of assumptions that there's a problem with linearity, there's a problem with equal spread, there's a problem with normality. And you should see that over here in the plots where we're starting to see the unequal spread right here, where we're seeing the non-normality of residuals. The line apparently picked up on something, probably just some sensitivity to the issues. And so does that make sense, Emin, right here? When you look at our plots, let's go back and look at our plot again. So 2 seconds. When you look at our plot over here, where do you see the biggest issues? And it should be pretty apparent. How many tests are failed right here, Emin? How many tests, first question, 1 through 3. Here's the first test. You notice it has the same value because it's just a linear regression. So the X variable is the model itself. Here's the second test. Here's the third test. How many of these tests are failed? These are the 3 steps. How many of these tests are failed? Here's the first test. Same p-value for the model and for the X variable. Here's the second test. Here's the third test. How many of these tests are failed? How many of these tests are failed? First test, looking pretty good right here. Second test, looking pretty good right here. Third test, not looking so good. How many of these tests are failed? Where we have evidence of a problem. How many of these tests come back with evidence of a problem? And so, yep, this one right here is where we see the problem. And then you should look over here for that one on the third plot. And look at this. You see like the extreme outlier up here especially. This is creating issues with the non-normality of the data. Technically you see it here, but you should look at the QQ plot for normality when normality fails. And so we see, does that make sense, Emin, right here? Like this is where the major problem lies. And so one suggestion we had was to take the log of it to help bring in these values. Now, we run into a separate issue right now, and this is why you have to know a lot of connecting issues a lot of times to deal with data. And why are we getting NaN? What does NaN mean? NaN means not a number. So if you look at the original values before we log 10 them, you'll see that some of them are negative. It looks like the minimum to me, the minimum value of this, because you can't log a negative number. You can't log a negative number. The minimum value is -999. So what I'm actually going to do to these values before log 10ing them is adding 1,000. And so when I add 1,000, let me double check my idea here. Good. When you add 1,000 to these values, and we know what the minimum is, the minimum value here is 1. And if you log 10.1, and this is just what we do in 474, someone typing this missing value is 999. And we could do that. We could put NaNs in there. That's another way to handle it. I've now turned these into 0. So I have a few options. I could create a data set. Let's do that option. Here is, let's go subset. Another option is to, if we say those were people who didn't, we're going to go to the corrected data, and let's go money in the bank, and we want not equal to 999, and that should do it right there. That should create the subset. And let's go to sub. So now we have a subset of people. If we look at the minimum vector of this, let's just do a histogram of sub. Too big, right? Oh, wait, what? Oh, wrong variable. So many ways to deal with data. Money in the bank. And it looks like now it's all positive values. Yeah, it's old-fashioned SPSS way, right? Yeah, no, that's -999. I think that's what someone did who recorded this survey when we took it. So truthfully, we might just want to remove them. So we could set them to 0, which now it's only 0 inflated data. Yep. So we have 2 ways of dealing with this right now. One, using our knowledge that it's SPSS, we could go here and create a subset where we remove them. I could have done it the other way with using square brackets, but my code is saying go to survey 09 corrected, go to people with money in the bank not equal to 9999 and select them. So I did the not equal to. A lot easier than giving all the other values. Or I could just say people who have greater than or equal to, oh, whoops. Oh, did I just do negative 999? There we go. There we go right here. All the people, hopefully I had greater than negative 999. Ooh. Let's do greater than or equal to 0. Because I think this is turning back 2 different values. There was another negative number, it looks like. It looks like there was another negative number in here other than negative 999. Last thing I want to see real quick is unique values. Let's go here to sort unique values. I love data investigation. Hopefully other people are having fun with like me. But the unique values of this, yeah, someone put negative 30. Or at least 2 people put that because we removed 2 extra people out. But I sorted the unique values of money in the bank, and there are someone. Yeah, isn't it weird the ways we recorded data? So you have to know all these different things, especially like past stuff, and like, okay, someone's using negative 9999 to be missing, negative 998, all these different things, and we finally reached the point. We finally reached the point where we can go in here and we can take our individuals and we can log this, and we don't need to add to this anymore. We don't need to do the correction to make them positive because you can't log negative numbers. We do have 0, right? So we need to add 1 to this. The reason we need to add 1 is because we can't log 0. Logging 0, there is 0. Yep, so we got the greater than or equal 0. And so now we do still have to add 1 to this. This is a 474 problem a bit. The reason we have to add 1 is because you can't take the log of 0. Log of 0 is infinity. So since, is it? No, it's negative infinity, isn't it? Or it approaches negative infinity. Yes. No. Log of 0 approaches. My brain is just breaking. Yeah, it should approach negative infinity, right? Yeah, because it's like log 10 of 0.0 is negative 2. Yeah, there we go. I'm trying to remember my mathematics. So we can't take the log 10 of 0 because that approaches negative infinity as you get more and more zeros right here. Unfortunately, you do have to understand a little bit of mathematical theory to sometimes take the log of stuff or understand why things are breaking. Like, why is this breaking? Why won't this give me returns? Because you're doing something mathematically impossible. So we're going to use our subset here. This turned into a much crazier problem than I would have expected. Like, this is... you could use ln. So if we do right here log, just doing the log, we'll do base e. I don't think the base matters so much. I'd love to hear someone make a case for a certain base. We could do ln. This is by default base e. So you can see here that log, if you do this, has the exp, the log base, natural log e, which is the natural log. So either way. So now we'll do natural log. There's the natural log of it right there. All this work for the regression. Let's go ahead and take a look right here at our regression. Okay, we got it, and now we've overwritten it. Okay, cool. I think we have it. Ooh. Well, I'll be. We actually got something going on right here. Oh, it's the statistical significance looks iffy, and it actually we do see a negative relationship with the log of money. So we've got here the log of money and a slightly negative relationship for those who drink more. Less data for those. But it doesn't look to be statistically significant due to the confidence bounds on the slope actually go to a positive number. I'm guessing a p-value of 0.065. That's my guess on the p-value. Let's go look at the summary of this model. And the p-value is... I should have went a little bit higher. Darn it. It definitely goes a little bit... oh, you can really see it back there on the positive nature. So the slope of the line And I was able to see that a little bit visually right here, that it would not be statistically significant for the confidence bands on the slope of the line, which is the mean of the line. So looking in here at the model, you can tell it's got that wiggle room where it could be positive or it could be negative. So visually speaking, the bounds on the true mean of the line. So what we're seeing here might just be due to random chance. And you do have some extreme points, so maybe high leverage points. We'll be talking about leverage here soon. We could always look at this with an influence plot, which I think you might have mentioned this earlier on. I mean, you got some high deleted residuals right here, and you've got some slightly high leverage points. There's a bunch of, see that point's right on the edge of it? I don't know. The size of the circle is the size of the influence. There's a lot of influential points. I mean, slightly influential, but it's the model, not the best of models. Let's check conditions on the model. New model, new conditions. Here we are. And once again, where do we only see issues? Where's the only spot we see issues in? Where's the only spot we see issues in? Everything else is fine and dandy. Everything else is actually amazing. Just totally awesome. Everything else is great. Where do we see the issues? Which we made it look better. Wish I had my other one instantaneously to bring up. Can you interpret the p-value for me? I'm struggling for otherwise to understand. Which p-value? The p-value, which p-value specifically? Because here's the biggest thing. All p-values tell us. Yeah, because you never meet it. I assume that's why you hate it, because it's like, all models are wrong. You're probably going to fail some assumptions. So are you talking about the p-value for the model or the p-value for the check regression? Yeah, the normality of the residuals, that's the problem. Now, all the p-values tell us is whether or not our results are statistically significant. The problem people run into, and this is a huge problem, is that does not mean the same thing all the time. You have to look at what you started out assuming. What was our starting assumption for the slope right here? What is our starting kind of naive assumption? Like when you look at the slope right here, there's a p-value right here that's very high or higher than we would like. And so that's not statistically significant. That's instantaneously when you see p-value, you say, oh, that's high, that's not statistically significant. Well, that's because what was the starting assumption with the slope of the line? The starting assumption with the slope of the line, and when the slope is not statistically significant, what does that mean? So, like, what does this p-value right here mean? It's, well, one, it's not statistically significant, but we're talking about this slope of this line right now. We'll do all the p-values on the screen. So what does that p-value mean right there? Exactly, because we start out assuming that the slope is equal to 0, a naive model, that there's no slope, and we don't have evidence to go against that. So, slope might be 0. That's not a good thing. That means there's no real relationship. We do not have statistically significant evidence that the slope is statistically significant, as in there is a slope. We think there might not be a slope because we don't have good reason to believe that. Now, one that we don't usually do is this one, which is very similar to what was just said. And this is statistically significant. But what does this tell us? And who cares about it? What is that p-value? Well, one, it is statistically significant. But what is that testing? That there is testing the what? Just go over to the far side of it and think about what that p-value is testing and what does it tell us? Like, what does it imply to us? Like, you're like, oh, well, we're actually testing this value and seeing if it's equal to this, and we have evidence that it is not equal to this because we are rejecting the null. So what are we assuming? What is that p-value testing? Just look at what follow the output over. We have an intercept that is not equal to 0. Great. Like, cool. The intercept, there is very convincing evidence that that intercept value, which is technically off the screen because that's where it's at. You know, it is right there. That intercept value right there, a little bit below 7 of 6.7 is not equal to 0. So there's evidence that the intercept is not equal to 0, but we care about the slope because the slope is the XY relationship. Not that they cause each other, but they're the XY relationship. We don't care about the intercept. It's cool. Intercept. It's a value. It's probably not 0. Really good evidence the intercept is not 0. Cool. When you get down here to these, though, you have to realize whenever you're testing assumptions in regression, we always assume that everything is what when we test the assumptions. Like I'm going to say, you know, is there a linear relationship between these points? Which means that the line kind of properly slices through the data. Like the line should be between these points, the line should be between these points, the line should be between these points. If you look, the line is kind of the average of these points. I mean, except in rare instances where it's not really far off, the line is doing a good job of going through the center of these points. It's really easy to see since this is integer data. And normal is one of the assumptions. This one tests the assumption of normality of the residuals, which is the hardest one to draw. The normality of the residuals assumption would state that at any given point for any given value of x, we would see a normally distributed pattern of the residuals, such as we would have 68, 95, and 99.7% of points within there. Maybe we should try to predict days by money. Yeah, we could do that here. We'll do that real quick next. We could try that. Predict days by money and use ordinal regression. Oh man, you're jumping into some more stuff. We won't do that today, but ordinal regression, yeah. Other techniques. There's always more techniques, and I can't state that enough. So yeah, man. I thank you for all your advice. Like, really, the question is like, what tool, what technique are you using? And the more tools and techniques you build, there's never one answer to these questions, because we could use principal component analysis. We could, for dimension reduction, we're not in high dimension data sets. We could use cluster analysis. Probably wouldn't apply here. We could use ridge regression. We could use, let's see here. You don't want to go to neural nets. You could use discriminant analysis. There's so many you could do. I'm trying to think. Support vector machine. You could do, what else? There's just so many things you could do. And it all depends. It all depends. And there's a really good package for that, the carrot package. The carrot package, the classification, associations, regression, training, or something like that. Carrot stands for a certain acronym. But there's a lot of really good ways to look at that. Just we need to meet assumptions. Yes and no. A statistician one time said to me, it's not how many assumptions you violate, it's how bad you violate them. So we have to ask ourselves, how bad is this normality of residuals here? You want to meet assumptions. But with the, yeah, here, I'll show you right here. You are correct, basically. With the 1R. I don't think I have it right now because I've reinstalled R recently. It should be that right there, C-A-R-E-T. And I am installing Carrot. So it was C-A-R-E-T. So the question becomes, and let me ask you this. This is a classic question I asked. So to go into what you just said right there, which of these would you prefer? You are going to predict people's, let's say, heart rate. And here you're going to predict people's heart rates using the following models. And so you're predicting someone's heart rate, like, like 65, 58, 78, people's heart rates. So here are your models. No, we can even put a naive model right here. So here's the naive model, which really doesn't have any assumptions. Naive model is just going to predict the mean of people's heart rates. So the naive has an RMSE, which we'll put naive RMSE of like 21, let's say. And this one has an R squared equal to, let's say, 0.98. This one has an R squared equal to something like 0.04. The p-values on these, p-value is equal to something like 0. It's going to be ridiculous. 1. And this one has a p-value equal to 0.03. And the naive is, it would have a p-value of 1, but we're not really going to test it. But then when you look at your assumptions, and here's the key thing I want to point out, the key thing. When you look at your assumptions right here, let's say your assumptions for like linearity, normality, technically normality's last. Just, it doesn't matter what order they come in, but. And so we're going to carry these down. And so your linearity up here, let's say, has 0.03, 0.40, 0.0, this is the hard one usually. And then this one right here is 0.85, 0.48, and 0.21. So the question becomes, which model would you use, Model 1 or Model 2? We'll kind of end on this question right here, a good one to end on. Or Model A or Model B. Model C just shows you the naive, and the naive is going to have an R squared of 0 because naive doesn't explain anything more than the naive. So which of these models would you use, Model 1 or Model A or Model B? Which of these models would you use just with this information alone? And you might say, I need more info, but I'm going to be inclined towards one model right here, definitely. Which of these models would you use, Model A or Model B, just with this information? You could always ask for more. You could say, let me see them, let me visualize them. But there's some major stuff in here I'm noticing right away between these two models. Oh, but think about your RMSE and look at your RMSEs. I mean, you're always welcome to disagree with me and be like, I would do this because you're in practice more than I am. So maybe Brian could be wrong on stuff. You never know. I'd go with Model A, but make the case for Model B, and I'll make the case for Model A. One problem we get into is statistical power. So maybe I didn't tell you this. Like I could add in this bit of information. Maybe this is a study done on 6,000 individuals. And as you mentioned, a big problem is it's very hard to meet assumptions. And when you have statistical power, it's very easy to detect problems with assumptions. Like more statistical power is the ability to reject the false null. Since all models are wrong, you're going to probably see the problems. And with such a large sample size, problems are going to persist as you try to fit. Now, one thing you mentioned yesterday is I would check. Yeah, sorry, I didn't mean to make it a trick question right there, especially. And I'll tell you why I'd go more towards Model A. Is Model A says that we typically miss predicting somebody's heart rate by 2. Like maybe we're taking into account their weight, their exercise, different things. Like we have a model that says, okay, we need to know someone's weight, their height, their BMI, which you calculate and all these things, certain measurements. And then we can make a model that predicts somebody's heart rate. And we typically miss by about 2 beats per minute. And then the R squared says we explain 98%, like our model explains 98% of the variation in their heart rate. But the second model right here, just even though it's statistically significant, does not seem practically significant. Its typical miss is very close to the naive, which is the no knowledge model, like the model that doesn't using, AIC. What if I told you, well, yeah, and that's Akaike's information criteria and the Bayesian information criteria. What if I told you the AIC of this model? So if we know how to interpret some AICs, the AIC of this model is -35, and the AIC of this model, so which model are you going to pick now? Because this is closeness to the truth. The AIC of this model is 100. So which of those are you going to pick? Model A has an AIC of -35. Model B has an AIC of 100. And AIC and BIC, basically just a Bayesian way of doing it, or the Akaike, famous Japanese statistician Hirtoga Akaike. One of our people in our department, Dr. Humphreys Bozdogan, who's from Turkey, -35. That's instantaneous for anyone who's AIC. Like when you look at that there and I tell you the AIC is -35, you're like, well, that one's lower. And it's a big difference. Generally, differences, yeah. Now you're more inclined for AIC. And these are the good things, like when you know these concepts, as we communicate right here, you're like, well, what were your AICs of your model? Which is a kind of a general way to talk about the closeness of a model, like how close it is to the truth, which is only an estimate. And we're going to try to go less towards overfit models because it has the penalty term. We'll talk all about this in our class. We've been talking about a lot of advanced stuff today on test day. But the AIC and AICC especially have penalty terms for the amount of predictors you're putting in a model. So the AICs are going to go less towards overfitting models, which is the goal, to kind of make the smallest or least set of variables that are going to explain the most amount of sums of squared errors. Like that's a generalization of how the AIC works. The goal is to reduce the sums of squared error with the least amount of variables. And AIC works with that exchange on few variables, high reduction in sums of squared error. So the lowest AIC can be is -infinity. So the lower the AIC, the better. Just mathematically, it is as sums of squared error approaches 0, we're taking like the log of it. I got most of the formula in my head up here. Like I know the good theoretical parts about the K predictors and all that good stuff. But the lowest it can possibly be is -infinity. And so the lower it is, the better. It's weird. You might think, well, 100's like 100 out of 100. No. The higher it is, the further your model is it's an estimate of how far we are away from the truth. I one time asked, well, how can we estimate how far we are away from the truth if we don't know what the truth is? It's just we're making estimates. We're just guessing. It's like you're like, I think I'm this far away from the finish line, and you can't see it. Well, then how can we guess? I don't know. We have a person in our department is from Turkey, Dr. Humphreys Bosdigan. Here we'll end with that. But this is really good talk here. We will be talking about AIC in our class. So especially if you're here watching and test day stuff, if you're like, what's all this stuff we've been talking about here? Well, we talked about the conditions, and I would probably go towards model A. We've got multiple lines of reasoning right now. Has a smaller typical miss, has a higher percent of variation in Y explained by X. It's super statistically significant. My dings against model A are there's problems with the linearity, minor problems probably due to the large sample size. There's problem with the normality of residuals, but hey, nothing's perfect and a lot of things have problems. Model B has really great assumptions. Yay, great assumptions, but the model really is bad when it comes to the model has a very large typical miss, especially when we look at the naive. It's doing about the same work as the naive, which is a no variable model. It's not using X's. The model also only explains about 4% of the variation, which does not sound very practically significant to me. Yay, the model is barely statistically significant, good for you, but the AIC indicates that this model is further away from the truth than this model. So overall, when we look at the pros and the cons against the models, which I've kind of highlighted right here, I think the choice, have I convinced you to choose model A? Maybe the AIC pushed you over the edge, and then we'll talk about Dr. Humphreys Bosdigan. Yeah, and so, but it's just a conversation. Like, I don't know, maybe someone will walk in here, or like Ronald Fisher will come back and say no. He'll say, nope, you fail the assumptions, you can't use it. It's just assumptions are so hard to meet. Some statistician's gonna be like, you better meet those assumptions. It's not good to not meet assumptions, especially the linearity ones, maybe a greater concern. The normality of residuals is going to be hit sometimes bad by outliers. So maybe, like you said, log it, transform it, try to fix the assumptions. Maybe you could say, here's, you know what, we're going to combine our answers. Tell me if you like this answer. Here's our final answer. We'll put all the music. My final answer is this. Let's work on model A. Let's use model A to kind of, let's use this. Let's work on this model. Let's see what we can do. Transformations, maybe a different subset of predictors, maybe a different regression technique. Let's see what we got going on here with model A and see if we can kind of get it in the direction. Then let's make sure we're not overfitting, because that's a huge concern. But let's take into account model A and move forward with that. Model B is trash. Fisher will come from the grave and probably, well, Fisher will be like, what you doing? What you doing to my statistics here? But I say we take model A, we keep working on it, we keep improving it. So we're really lucky, especially at the University of Tennessee. We have Humphreys Bosdigan. We have many, many great teachers. But Humphreys Bosdigan has him college business. I'll bring him up right here. Amazing, amazing teacher. I can show him in the background right here. But great, great guy. Super awesome. Has helped me out a lot. Definitely helps me with my understanding of topics. I've taken a few classes with him, but that's Humphreys Bosdigan. Yep, Mackenzie professor in business. So University of Wisconsin, University of Illinois, University of Chicago, CV right here. So we can take a look at his CV. Yeah, just amazing stuff. Dr. Humphreys Bosdigan. And if we look at Akaike, Bayesian modeling and economics, there's a problem with the test. What is the problem with the test, William? Please tell me. Born, Turkey right there. He's got a lot of info. He's got his, what is the test? Turkey is out of neighborhood country. I don't know what that means. And then he worked with Dr. Akaike, which is something amazing. Oh, is your neighboring country? That's awesome. Where's Dr. Akaike right here? If I spell Akaike correctly, then we'll see it. I'm worried about the problem with the test. Here it is. So he's worked a lot with Dr. Akaike. He actually presented to him, and he actually went to Japan, visiting research fellow. Hirotoga Akaike. Akaike. Got it. So yep. There he is with Dr. Akaike, and a lot of work. If you look at everything we hear with Akaike, a lot of major work with Akaike. Really great guy, Dr. Akaike. Very influential in the statistical world. Super great stuff. I'm going to have to see what's up with the test. On my number 25 comma was being added to the answer after I clicked it. Yeah, just tell me, I'll fix it. I think it actually does that. When I put in the correct answers, it put in a comma. I noticed that too. On my number 25 comma was being added to the answer after I clicked it out, but only restarted. Yeah, I think it does that by default. Don't worry, it kind of like made me worrisome too as I was putting in correct answers. Trying to think which one that is. I was looking over everything last night and I was putting in correct answers. More than 8 pages CV. It's quite. Oh yeah, we got a lot of. Could you walk me through? Yeah, Caroline, good to see you here. Let's go. Can you tell me which question that is? Oh, the homework. The homework doesn't change. It doesn't change. Caroline, great to have you here. Thank you for swinging by. Anytime you see me talking here, Caroline, just feel free to throw a question in the chat. And you asked the question at the perfect time. Not that there's not a perfect time, because I can immediately start doing the question because we're just here in a little break right now. But when you see that we're live on YouTube right here, Caroline, just be like, hey, Brian, can you explain this problem? If we're currently working on a problem, I will finish up the problem. If we are just in a little bit of a break right here, I will immediately go to the problem. So I am loading up. This is question 4 on chapter 5, homework part 2, due tonight. So homework part 2, let's go here to replace questions. I have to go to replace. Question number 4. It is loading in the background, and let's take a look at it right here. Is it the steer weights problem? I think it's the steer weights problem. And I think I'm typing the numbers in wrong. Let's take a look. Here we go, going over to the steer weights problem. Okay, so this problem right here is using the 68, 95, 99.7 rule. So we need to go ahead and start using the normal curve, the Gaussian distribution as it's called, the bell-shaped curve. And we're going to use the David M. Lane applet. Now, a lot of people, awesome. Thank you, Caroline, for swinging by. A lot of people use z-tables. I'm not a fan of z-tables, and I'll tell you why. Because z-tables have certain values on them. You can't go to a z-table and just say, well, I would like to see this value. Because we're going to go right here, and we're going to put in the values we have on our curve. By looking at the question itself, and let's go here to the question. The question says, steers weigh on average 1,153 pounds. So this right here, Caroline, what is this part of the answer? This part right here, let's circle it, is the what of the normal curve right now. Like when I draw a normal curve, that number right there is going to be at the what of the curve. Horrible normal curve. That number 1,153. I think about 8 or 10 points. So you want to shoot for like a 40. It'll like that'd be great to make a 40 before I'll be going in and grading supplier after this. So I think it shows you your grade. Just doesn't show you the right answers yet. So what is that 1,153 in that notation? General notation, it looks like this. So what is that 1,153 right there of the distribution? That tells us the what of the distribution. So that 1,153. You're welcome anytime, William. What does that 1,153 mean? So it's saying normally distributed with mu and sigma. Mu sounds like I'm saying something starts with an M. The 1,153 is the mean. Great job right there, Caroline. Excellent work. That is the mean. And then what does the 81 tell us of the distribution? The 81 is a measure of spread. And the measure of spread is the what of the distribution. Like each time we're going up by this amount. Like we'll go up and down by that amount. So you can just put 2 letters. I'll know you know what we're talking about here. The sigma something. The sigma tells us the what of the distribution. And this is what David M. Lane will do for us. It'll plot this out. The standard deviation. Great job there, Caroline. We're going to throw some points out to the chat. So we haven't thrown out many. We're going to throw some 50 points out. MuBot's here in the background giving everyone points. So that's going to give us the standard deviation. 1, 1, 5, 3, and 81. 1, 1, 5, 3, and 81. And one of the best things to do is put it into both. I'll explain the difference right here. Now, this is when we know the percentage. As in, I could say to you, like, what's the top 10% of steer weights? If you notice, it's graphing the top 10%. This is when we know, like, an amount, where I could say to you, what percent of steers weigh above 1,180 pounds? And that's the percent of steers that weigh above a certain weight. So this is when you are given a value and you want to find the area, as in what percent of steers weigh above 1,180 pounds? Well, that's 36.94%. This is when you are given an area, as in like a percentage on the curve, the top 10%, and you want to find the value at that area. So it's value from an area. So I'm giving it the area, like shade for me the top 10%, and then tell me, where does that value begin at? So we go right here and we look at the question, what's the highest 10% of weights? Well, the highest 10% of weights needs to be up here. Now, an important thing to note is that the highest 10% of weights, can I copy paste that? The highest 10% of weights is going to be the 90th percentile. So make sure you know that, especially that the highest 10% of weights, because we're talking about the top 10%, that is the 90th percentile. The highest 10% of weight is 90th percentile. Now, you have to be careful when you're using the applet because you can't just type in 20. What percentile am I at right now? On the graphic, which I'm currently at 12,021 pounds for steer weights, what percentile am I currently at by graphing the top 20%? The top 20% of the curve, which we want the lowest 20%, is the whatth percentile of the curve, and you go from left to right to read percentiles. So think above here is 20%, and the answer should be below here. We'll tell you the percentile. So what percentile are we at on the curve? We don't want this answer below. We actually want the 20th percentile, but right now visually I'm showing you the whatth percentile on the curve. So percentile is always the area below a point. You'd love to be in the 99th percentile on the test. That'd be awesome. The 80th percentile, great job right there. So if we want the bottom 20%, we're going to go down here, and this is the 20th percentile, or the 20th percentile of steers. So this is the value for the 20th percentile. We're just going to copy paste it over here to our question. And we're going to delete down to 1 decimal, make sure to round if appropriate, and there's the answer. Now, the middle 40% can be found a few ways. The middle 40% is going to be where 40% is in the middle. And I love the applets for this reason, because we can just go right here. But here's the tough question. If this is the middle 40%, what percentile is right here? And this definitely leads into tougher test questions. I want to know, so see if you can find this out, and I'll draw some answers on here. What percentile is this? As in right there, if this is the middle 40%, then what percentile are we at? Which is not quite what this is asking, but what percentile is that? And we'll draw in some helper answers. Due to the law of symmetry, I know that there's 60% on the outside. So what percentile are we at right here? What percentile would that be at? And you can use the numbers marked on the curve. Close, close. Good guess right there. Let's throw some 20 points. You're very close. Now remember, percentile is the area below the curve. So if you go to the area below this, double check you're super close. So, it's disappearing it. I can't shade the whole thing. Here, I'll shade around it. That's kind of the answer right there. So adjust your answer slightly. Remember, percentile is the area below a point. So what percentile is this technically? Percentile is the area below a point. So when you think about the area below a point, what percentile would this be? You're super close. So when you say you're at the 70th percentile, that would mean 70% of observations are below you. So like you want to be at like the 90 or 95th percentile on tests. You don't always want to be like, if you think about like, especially children growing up, if you're in like the 99th percentile of weights growing up, that means you're quite heavier. Maybe you want to be closer to like the 50th, 60th percentile, be closer to the mean. Or maybe you want to be like a sports player and you want to be like the tallest and heaviest person in your group. So it all depends. Like, what's the goal right here? What is the goal with a distribution? Where do we want to be? Do we want to be on the upper ends of the distribution, the lower end of the distribution? So what percentile would this be? And we just do the area below. So we need to take and add these two numbers right here. And so if we add these two numbers, we can find the percent of area below this point, and that would make this the 70th percentile. So this would be the 70th percentile right here, because we're just going to add those two numbers. So that'd be 70% of the observations are below this point. As we can see here, from 40% in this inner region and 30% right here, leading to 70% below the point. Great job, Caroline. Excellent work. Excellent work. And so the two numbers we get for this are the following. The two numbers we get are here. I'll round afterwards in a second. And the second number is right here. And we will round this number if we go back to it. Do you have any more questions, Caroline? Feel free to ask. It says to round to 1 decimal, that would round up. It says to round 1 decimal, that would round down. And we've done it. Does that make more sense right there, Caroline? Going over this question right here. Feel free to always swing by. Thank you for working on these early. Whenever you're stuck, just be like, hey, I'm stuck on this. I've got videos I can send also if I'm not currently live. But I've got a lot of videos going over different things. But if you come in, I'm live, you can also just be like, hey, I'm stuck on this. How do I solve this question? What does it mean? How do I use the David M. Lane applet? Lots of practice right here. Feel free to say any other questions. We'll put on a little music right here. Awesome. Congratulations. Excellent work. Once again, we just haven't had as many 201ers swinging by. And I marked these videos afterwards so you can tell if something for 201 was done. But Caroline, feel free to jump in, ask questions. Hey, Brian, I'm stuck on this. Explain to me how this works. And I will walk through problems or explain concepts, especially when it comes time for test review next week. We'll do some test reviews and we'll do Kahoots for 201. So glad to have everyone here. We'll be back tomorrow, but when you're stuck on work, just swing by office hours and we'll get it done. Until then, bye for Puppet Shark. Where you at? Bye for now, everyone. We'll be back tomorrow. Bye.